Now let's make the transition over to wave motion. We're looking at some ripples in the pond right here. You can see that we have some frequencies and oscillations and everything like that. So it's related quite well to the simple harmonic motion I've talked about previously. If I take my hand and I grab hold of a rope and I move it up and down, essentially reproducing simple harmonic motion, you know that the rope is going to move up and down, and it's actually the wave is going to travel along the rope. It's important to kind of note that the rope itself is simply going up and down in that direction right there. The wave is going to be going in that direction right there, and the velocity of the rope is not going to be the same as the velocity of the wave, but also the particles don't have to move in the same direction as the wave. If we look at the rock that's been thrown into the pond, the water is simply going up and down, but the wave is going in the outwards direction. All waves are going to transport energy. I'm going to talk about two types of waves here, but both types are going to transmit energy. How do you know that they transmit energy? Well, if you were attached to this side of the rope and I pulled it up and then pulled it back down, you can see that we're going to have a wave. That wave is going to travel. Remember, the velocity of the wave is going to be in that direction. The particles just move up and down. Then at some later time, you're going to feel the pulse of that wave. You're going to feel all of that energy. If the motion was continuous, if my hand was continuously driving this guy in simple harmonic motion, then you would see this wave look sinusoidal, as it did on the last slide. A lot of the characteristics of wave motion is going to be very similar to what we've already observed in simple harmonic motion. If we look at a continuously driven sinusoidal wave, we're still going to have an amplitude, which is going to be the distance away from equilibrium. We're still going to have a frequency and a period, where the period is going to be the crest-to-crest time. So we have the period. One thing to keep in mind is the period is in terms of time. A new thing that we're going to have to worry about is the wavelength, which is also going to be measured from the peak to peak. However, the wavelength is going to be in terms of distance. Thinking about ripples in a pond, we're going to have both distance and time. Of course, we know that distance and time can be related to each other through the velocity. The velocity is essentially going to be the distance divided by the time, or the wavelength divided by the period. Knowing that the period is 1 over the frequency, we can get one very important equation that's going to describe the velocity of a wave in terms of the wavelength and the frequency. Wavelength unit would be meters, it's distance. Frequency and period you're already familiar with. Velocity, meters per second. Two types of mechanical waves I'm going to talk about is going to be transverse and longitudinal. Both of these do transmit energy. The real difference between them is going to be the motion of the particles. Transverse wave is going to be this top one right here, where if I take a slinky and I wave it up and down with a simple harmonic motion, I'm going to get waves where the particles are moving up and down. So in that case, the particles are going to be up and down. However, the wave is going to travel in that direction right there. So the motion of the particles are going to be perpendicular to the wave direction. It's a transverse wave. Another way I could transmit energy along the spring is to keep it level and simply wiggle it back and forth like that, again with simple harmonic motion. In this case, the wave is still going to travel in that direction, although in this case the particles are going to be moving back and forth. They're going to be parallel to the direction of the wave. It's important to note that the particles don't travel all the way down the slinky with the wave, it more or less stays where it is. It just wiggles back and forth, and I can set it up pretty much the same way and talk about the same types of properties in terms of wavelength, period, and so on and so forth. Essentially, I'm going to have regions of compression and regions of expansion, and then regions of compression, regions of expansion, and I would define my wavelength to be the distance from the compression region to compression region. Same types of thing with period and frequency. Turns out that sound waves are going to be longitudinal waves, not transverse waves. If you consider your computer speakers pouring forth the relentless drone of my voice, the speakers have this membrane that's going to essentially be wiggling back and forth. It's going to be forcing air particles together and then essentially pulling them apart. The air molecules are moving back and forth just a little bit. The wave is going to be traveling in that direction right there, and we're going to have regions of compression and regions of expansion that are going to be moving outwards. An important equation describing the speed or the velocity of a wave is going to be related to, for a transverse wave going down a chord, it's going to depend on the tension of the tension on the chord divided by this little guy called mu, where this mu is going to be equal to the mass per unit length of a wire. What this is really saying is if you increase the tension on a wire, then the velocity can essentially go up. If you increase the mass of a wire, then that's going to increase this mu, and the velocity is going to go down. It's harder for the wave to go down essentially because there's more mass, there's more inertia to overcome. And the same type of argument with the length. Example 1111 gives us a little practice using that, where we have a wire that's 300 meters long with a mass of 15 kilograms, and under some tensional force of 1,000 meters, we're asked to figure out the speed of the wave. Simply going to be using that equation right there, where we have tension of 1,000 newtons. The mass is going to be 15 kilograms, and the length is going to be 300 meters. So we can calculate the speed of a wave that goes down it to be 140 meters per second. So let's talk about the energy that's being transported by a wave. We know for simple harmonic motion that the energy was equal to 1/2 multiplied by k multiplied by the amplitude squared for, say, a mass on a spring. It's not going to surprise you that the energy transmitted by a wave is also going to be proportional, that's a little symbol right there, to the square of the amplitude. Obviously, if a wave has a larger amplitude, it's going to have more energy. Turns out that it's actually more useful to talk about intensity because we have these waves, they're carrying energy and they're arriving over a certain time interval. So if we define the energy per unit time, and also we have to consider the area of the wavefront. So how large is the wave that is coming at us? So think about the area of the crest of the wave, for example. Then the ratio of this energy per time in the area is going to be the intensity. We know that energy per unit time is also going to be power. Power having a unit of watts, area having a unit of meter squared. So the units of intensity is going to be watts per meter squared. Because the energy was proportional to the amplitude squared, and we have energy right here, the intensity is also going to be proportional to the amplitude squared. Because the intensity was equal to the power divided by the area of the wavefront, if we think about something like a wave that's going out in a spherical sense and we have some power at the source, the wavefront area is actually going to become larger and larger and larger as the wave spreads out. So the area is actually going to be continuously increasing. We know that the area of a sphere is going to be 4 pi multiplied by the radius squared. We're going to have power on top. What we can kind of see is the intensity is going to get smaller and smaller and smaller as the radius gets larger and larger and larger. So if you consider a point source, say a radio, putting out a certain amount of power, the intensity you hear with your ear is going to get smaller and smaller and smaller, proportional to the square of the radius as you walk further and further away from the source. Now let's take a look at what happens when waves hit obstacles. We're going to have two types of obstacles we can hit. We can have it where the end is going to be fixed or tacked down to the ground, and then we can have the type where it's going to be free to move. Let's consider the fixed case first, where we have a wave moving in that direction. As the wave approaches the tack, it's going to essentially start to get smushed down, and this tack is really going to be pulling quite hard down on the wave right here as the rope tries to lift it up. Because of this, it's going to whip that rope down, and the wave is going to start to bounce back, only now it's on the bottom side of the rope, and it's going to essentially be inverted. It's going to be upside down and moving away from the fixed point. You can try this on your own if you don't believe me. In the case where the end of the rope is free to move, the wave is approaching it, and then here there's no tack to pull down on it, so this free end of the rope just starts to naturally come down again, and the wave that is going to be reflected is going to be, in this case, upright. If we consider a rope that's going from a light section to a heavy section, we have some wave coming down there, what's going to happen is it's going to, the same type of thing, it's going to be partially transmitted and partially reflected. The heavier section is going to pull down on the rope, much like the tacked down version from the previous slide. We're going to have an inverted reflected pulse, but some of the pulse is going to be transmitted, recalling that the velocity was equal to the square root of the tension force divided by the mass. This is a much more massive section of the rope, so the wave speed is going to be lesser because we have a denser medium. It also means that the wavelength is going to be shorter. We can look at two-dimensional waves, again looking at reflection and transmission. To do that, we need to talk about these wave fronts, which are essentially going to be all the crests of the wave. So here we have a spherical wave. Think of ripples in a tank. All the crests are going to essentially more or less fall along a circle, and we're going to now call them wave fronts. If we take a line and we draw it perpendicular to the wavefront, it's going to be called a ray. It's also going to be the direction that the wave is propagating in. Simplest possible case is just to have waves that are lined up straight up and down like this. In that case, the wave is going to be propagating in that direction, and the ray is also going to be in that direction. It is useful to talk about that, or to talk about rays when we talk about reflection. If we consider some waves going onto the shore, you're out fishing and you set out a wake, the waves are going to be roughly linear coming into the shore. What's going to happen is the incident ray is going to come into the shore, and the angle of the reflected ray is going to be equal to the angle of the incident ray. So what that means is the waves that are bounced off of the shore are going to have their wave fronts along in that direction. So we can say that the angle of the incident ray must be equal to the angle of the reflected ray. One important caveat is this angle is relative to the normal line to the shore. So this, if you take your shoreline right here and you draw the line normal to it, as I've drawn right here, the angle of incidence is measured relative to that, and the angle of reflection is also measured relative to that. Chapter 23 is going to talk about this concept in more detail. If we consider waves that are two waves on a string, they can interfere with each other. They can interfere with each other such that they add up, or such that they cancel out. Considering this first case right here, they're going to cancel each other out. They're going to exhibit what we call destructive interference. We have that wave moving in that direction and wave moving here. At the instant that they overlap, they're going to essentially subtract. Amplitudes are going to subtract, and we're going to have no wave visually present. And then the pulses are going to continue about their merry way, because energy cannot be destroyed. If we consider two pulses that now have the same amplitude, and they're coming at each other, then at that particular second they're going to add up, and we're going to have a wave with twice the amplitude, and then the waves are going to continue about their merry way. For this particular case, what happened was the waves simply had equal but opposite amplitude. So this idea of how waves can interfere or add up or subtract out is going to lead us to the last important idea, which is going to be the idea of standing waves. Essentially, if I have a string that I'm yanking on one end and it's fixed on the other end, I know that if I yank on this string, that the reflected wave will be in the opposite direction, or negative amplitude. And if I timed it just right, I could be shaking up and down such that these two waves would add together in this case right here, and subtract out in this case right here, and then they would also add together over there. If I shook it even faster still, then my wave plus the reflected wave could have three parts where they add together, and then two parts where they interfere and subtract out. So these parts where the amplitudes are going to add together, they have a name called an antinode. It's going to also have nodes, which are where the amplitude is always going to be 0. It turns out this concept of standing waves is important because this is how musical instruments work. If I now fix both ends of my string right here, the waves that are going to resonate are going to be ones that meet the criteria on the last page. I'm always going to have a node at that end, and I'm always going to have a node at that end. In the middle, I can have nodes and antinodes based on whether the waves that are traveling back and forth are constructively interfering with each other or destructively interfering with each other. Physicists are going to call these frequencies the resonant frequencies of the string, much like I talked about resonance with simple harmonic motion. Musicians are going to call these fundamentals or overtones, possibly harmonics, depending on how scientifically oriented the musician is. It turns out that the first possible harmonic it must be fixed on both ends, have nodes there. It's going to have an antinode right there. and the length of this guy is going to be half of a wavelength. The reason for that is because the wavelength is going to be the time for one full oscillation. So this distance right here is going to be one full wavelength. So the length of this is going to be half of the wavelength. This is going to be called the fundamental, or first possible harmonic we can have on the string, and it's going to depend on the mass of the string as well as the tension of the string. That's going to affect the velocity of the wave, as we already know. The second possible harmonic must have nodes at both ends, is going to have a node in the middle, and we're going to have antinodes here and here. This is going to have the length be equal to one full wavelength, so one full up and down of the wave. This is going to be called the second fundamental, and because it's traveling at the same velocity and all that good stuff of the first wave, those are properties due to the string, it's simply going to be twice the fundamental frequency. So if you find out what the fundamental frequency of a wave is, the second fundamental is just going to be 2 times that. Same thing for the third harmonic. It's going to have, in this case, 2 nodes in the middle, the antinodes there, and there. And this is going to have a length of 3 times the wavelength. So in general, we can write all of the possible frequencies of a string instrument, a string that is fixed on both ends, to simply be n multiplied by the fundamental frequency, where n is going to be 1, 2, 3, and so on and so forth, as you can see from the previous slide. The wavelength that is set up on the string is going to be 2 times the length multiplied or divided by n, where n is going to be 1, 2, 3, and so on and so forth. This is about the time where I should work example 11-14, but I feel like this lecture's gone on for a long time, so please do work example 11-14 before coming to class.